We've done one example of working with energy conservation. Now I'm going to do a second. I'm thinking that after you've seen a couple of these, that you'll have enough of a framework for this that everything will just kind of be natural. Here is a new problem. I can approach this with energy. Here's kind of what I need. So for this one, what I'd like to do is have my potential energy source be a spring. Now I'm going to do this one actually maybe with a ramp and a spring so that you can see how that kind of works both ways. So I've got some little section of wall. I've got a spring. Let's give this thing a spring constant. K equals, we'll go 100 newtons per meter. Not much of a spring. We'll put a block here. Say mass equals 2 kilograms. No friction. We haven't quite gotten around to that yet. And I'm going to start this thing out by compressing my spring by 1/2 meter. I'm going to then release the spring, and I'd like to find two different things. I'm going to find one, maximum speed, and then two, how high up the hill is this going to make it? So first, I'm going to say I have 3 different points. I have point A, where we are compressed, or at least the spring is. Point B will be right here. This is my launch. And then we'll have some spot up here, point C, where we've reached our maximum height. So for question 1, I'm looking for maximum speed. I'm looking from point A to point B. Let me start doing that. Before I had initial and final, now I'm just going to talk about A and B. I can break this problem into 2 separate mini problems, one that is just the launch, in which case B becomes the final, but then the second problem where we go from the launch to the maximum height, we can say the final from the first problem becomes the initial for the second. Either way you want to look at it, it's completely fine to just say from A to B. So I'm going to have potential energy, kinetic energy, and total, and start making my table. Alright, potential energy, let's see, I'm starting compressed, so I'm going to have 0 kinetic energy to start. In the end, I'm launching, so I'm going to have 0 potential energy. My final kinetic energy, 1/2 m v final squared. My initial potential energy. This time I don't have the MGH type of energy. What I have is spring energy. So I'm going to have a 1/2 k x squared kind of energy, and that's my total. 1/2 k x initial squared, 1/2 m v final squared. Or if you don't want to use initial and final, and maybe we shouldn't, I can use A and B. Then we'll keep going. So we're going to set these equal to each other. 1/2 k xa squared equals 1/2 m vb squared, and start solving. We can cross off the halves. We can't cross off a mass, so now the mass actually matters, and that should make sense. Right, if I have this spring and I stick a 2 kilogram block on there, I'm going to get some kind of a resulting speed. If I stick instead a 200 kilogram block there, it's not going to move as fast. So it makes sense that mass is not going to cancel out of this one. When I solve this, I'm going to get VB equals K over M times XA squared, all under the square root, and I can plug in 100 newtons per meter over 2 kilograms times 1/2 meter squared all under the square root, and I get 100 over 2 is 50. A quarter of 50 is 12.5, and the square root of that is 3.5. So I get 3.5 meters per second. That's my launch speed. The second part, how high does this block slide up the hill? I can do this a couple different ways. I can either look from B to C, so I'll draw a line here just to keep the problem separate. I can either look from B to C, which is completely fine, going from the launch to a maximum height, and my energy is conserved, and that works. Or I could even say, you know what, all the energy I had at the start, if the energy at A is the same as the energy at B, and the energy at B is the same as the energy at C, then I could go straight from A to C. Either of those is an option. I'm going to go actually and just add an extra column into here. Because my total energy is the same anyway. So my potential energy at C, mg, and I am looking for my final height. My kinetic energy at C is 0 because I'm coming to a stop. If I still have some kinetic energy, that means that I am not at my maximum height yet, or I'm not there anymore. I guess I could be on my way down already. So I'm going to get mg hc. I can set my energy at C equal to my energy at B or my energy at A. I'm going to choose to do A because when I did my energy at B, I found this V. This 3.5 is really 3.536 meters per second, something like that. So it's a rounded number. It's going to be more accurate if I go straight from A to C because I'm not working with any rounded numbers. I'm just working with given numbers. So when I do that, if I say A to C, I'm saying half k xa squared equals mg final height. I'm solving for that final height. So I get k xa squared over 2 mg, and I can plug in. When I do that, I get a final answer of 625 meters. This thing is going to go 62.5 meters, or 62.5 centimeters, sorry, up the hill and come to a stop. That's how I use energy conservation with different forms of potential energy.